Hello everyone, this is Tasnia from Department of Computer Science and Design, and we are going to see about the fundamentals of computer networks, and that we are going to see about the network layer topic of IPv6. Before that, we have seen about the IPv4. So here we have we'll start with our puzzle. Like we are connecting with the reality. We have to empathize the problems. So you ought to own a smartphone, a laptop, a smart TV, a smartwatch, and a smart fridge. So does every other person on earth? How does the internet give each device its own unique identity? Okay. So here we have 4.3 billion of maximum users of IPv4 address. That's forever. And 8 billion plus people on earth, each with multiple devices, and 29 plus billion IoT devices by 2030, like sensor cards and wearables, etc. So the internet is running out of addresses. Like IPv6 is the only solution. Why IPv4 is running out of stream? Here the core problem we have to see. We have set off IPv4 limitation like address exhaustion, no real-time support, no security header overhead. And in IPv6 there are 2 into the power of 128 address. Like here it is a 2 to the power of 32, 4.3 billion address. We have used them all. So here we call it a 340 undecillion unique address we have, effectively unlimited, which is the flow labels built-in support for real-time multimedia traffic. And IP6 are native in encryption and authentication baked into protocol. And we have the simplified healthy steps like fixed length based on the extension of the header. So here is the IPv6 address and its structure and its notation we call like 128-bit address written in hexadecimal colon notation. Like FDEC, we call it as, which is a network prefix, and 0074 and zeros can be compressed, and there will be 0FF which is a provider ID, and FFF is the node ID. So here the abbreviation rules: rule 1, dropping leading the zeros in each group, which is 0074, which leads to 74 we consider. And replace consecutive all zero groups with only ones, like if take the same way here. Okay? This is the structure and the notation of IPv6. So we have IPv6 multiple types, categories based on categories and its scope. We have something called as unicast, multicast, and anycast. Like unicast is nothing but one-to-one delivery. There are 3 subtypes: global, link, local, site local. It's like sending a letter to one specific house. Multicast is one-to-many delivery packages sent to all members of a group, like a TV broadcast to subscribe to users. And anycast will be one to nearest delivery sent to nearest node in any group by routing metric, like calling 911 router to nearest available responder, etc. And here we have one question like IPv4 introduced short-term fixes like NAT, CIDR to delay address exhaustion. If you were a network engineer in 1990s, would you have pushed for immediate adoption IPv6 or continue patching IPv4? What are the trade-offs? First, we have to think like reflect individually on the trade-off, consider cost, backward compatibility, urgency. And then we have to pair, discuss with your neighbor, share your reasoning. Did you agree there? And sharing, which means comes under group of share key in the instructor summary, etc. So here is the packet format we call it as like we have a basic base header fixed 40 bytes plus optional extension header plus payload. So version 4-bit always is for IPv6, and priority 4-bit traffic class helps routers prioritize. And flow label, which is a 24-bit tags packets of same flow example video stream, and the payload length the size of data plus extension headers up to 65,535 bytes, 65,535 bytes. And the next header will be 8 bits, which is a type of next header: TCP6, UDP17, ICMPv6. The hop limit will be 88 bits, like same as TTL and IPv4, decremented at each router. Here is a quick concept check we can do. Like question 1 is expand as abbreviated IPv6 address will be 015 colon is to 1 is to 12 is to 12 into 13. Like count the group, how found how many zeros are replaced. Okay. Then there is a transition from IPv4 to IPv6. The device runs both IPv4 and simultaneously, like dual stack, and tunneling will be the encapsulator inside IPv4 packet to traverse IPv4 only. Then header translation will be NAT64, like a translator converts IPv6 address to IPv4 headers at the border. Here we have the industry case like Google IPv6 rollout. What is the scale of the problem we need to analyze and measure the improvement and what they did to overcome for that and lessons for the engineers. Next one is evaluating IPv6, which is a trade-off and limitation like massive address space and no NAT needed, built-in IP seconds, slow adoption, longer address, no backward compatibility. Here is a mind map to go overcome the network layer, how it was getting split. So what are all the things we have seen here is every device need an IP, billions of devices, finite IPv4 space equal to crisis. IPv4 has three core flaws like address exhaustion, no QoS, no security. IPv6 where 128-bit address, hex colon notation, Unicix, unicast, multicast, anycast, which is a types. And here it's for prototype will be 40-byte base header, which is chained extension header, which is clean and extensible design. And dual stack transition faster than IPv4, no NAT, and slow adoption in the real change. So here is the main key takeaway, the extension of internet addressing. We can go through this slide. Here is the reference of the book we can reference and the website reference we can go for jigs projects.